As promised, a little look into cache associativity and how the cache works internally to some extent. So, given an address of 64 bits, it's from a cache's perspective, this is divided into several pieces. First, the cache always deals with memory in terms of 64-byte chunks or cache lines. So the first 6 bits is treated as an offset into the cache line that we're currently dealing with. For the rest, we don't care. The cache doesn't worry about the offset. And then it's further subdivided into sets of cache lines. In this case, on pages, we have 8-way associative caches, or at least that's the best we could find out in class. With an 8-way associative cache, we can fit 8 different cache lines in one set. So therefore, a 32 kilobyte cache, that would be 512 lines, 64-byte lines. And these lines are then divided into 64 sets, each of which can hold 8 different lines. Right, so for 64 sets, the S here becomes 6, right, for 2 to the power of 6. Right, 64 different sets. Okay, so this set index decides, the set index of the address decides which set this particular part of memory, this particular address, needs to be in. There's no choice there. It can only be in one set. And then finally there's the tag, and that's used to just say, oh, which part of memory was it? Right? So this determines where in the set, this determines where within one cache line, and this is basically the remainder saying which one. To identify the cache line, when we're looking for the contents in the cache to see, do we even have it in the cache, then we need to find the correct tag. Right, so as a result, any address any tag is separated by the combination of these two, so 6 plus 6 in this case, 12 bits, or 4096 bytes. So if you have a different tag, it'll be a multiple of 4096 bytes away. It's a little confusing, so I made a drawing as well. One way to think of it is this. So for our 32 kilobyte cache, with the 512 different sets, the end result is that we have sort of a spacing of this L1 overlapping the main memory here. So the first cache line in the L1, the 0th cache line, it can hold the 0th byte of memory, and then it can hold the next byte of memory it can hold is 4 kilobytes away. Right? You look back here. The set and the set index and the offset defines within this 4 kilobyte chunk where in the cache we should be, and then the remainder, the tag here, decides which one of all these possible red dots, and it continues, of course, it should be. Right, so this one here can only hold 8 different ones, but can only hold these relatively far spaced parts of memory, 64 byte chunks of memory. 8 different ones as an 8-way associative cache. Something similar is true for the 32 kilobyte, sorry, the 256 kilobyte L2. If we have an 8-way associative cache, then again, the spacing will be 32 kilobytes. So now the first byte of the L2 can only hold these 64 bytes. And the first line of the L2 can only hold this line here, or this line here, or the next one, and so on. Right? So spaced 64 bytes apart. And again, for the LLC, so here we have a 16 megabyte last level cache, which means the spacing is 2 megabytes apart. So why does this matter? Well, usually it really doesn't. If you're accessing memory, say, sequentially, we're dealing with a picture, let's say, and we're just copying a picture from here to there, or maybe it's a little bigger, right, somewhere in memory, then we're going to end up touching all the bytes within this 4 kilobyte range, meaning we're using the entire L1 cache, probably all the bytes in the 32 kilobyte range here as well, so on. That's fine. So if anything where we're scanning or using large chunks of data, that's good. If you're accessing random addresses, same thing. It's probably going to be scattered all over the cache, so we're going to get pretty good usage out of the cache. The problem happens if we start having uniformly spaced and sort of unfortunately aligned accesses. It's pretty easy to see here for the L1 cache. It's 4 kilobytes. That's a page. So imagine our algorithm, our program, is touching only the first byte on every page. What's it doing with the first byte on the page? I don't know. I don't have a good example at the moment. But if we are only writing to the first byte of the page, that means we're only touching the first cache line of that page, which in this case is this red one here. So it may look like we have a 32 kilobyte L1 cache, but the addresses that we're accessing, because of the way they're spaced, can only go in the first line of the cache. So we're wasting the rest of the cache, essentially. So we went from 32 kilobyte cache to 8 times 64. So that's 512 bytes of cache. We can fit 8 different lines in our entire cache. Problem isn't quite as severe for the L2, right? Because here we're 64 byte spaced, so we'll get to use one of the lines here, one of the lines here, and then one more here. So we got 4 lines in the L2 cache times 8, so 32 total that we can fit in the L2 cache. Right? Still a tiny amount compared to the full capacity of the cache, and so on. You could imagine it gets worse if you have spacing that's further than 4 kilobytes. If we space our accesses 16 megabytes apart, then, well, all accesses will fall, if it's the first byte again, 16 megabyte spacing. All accesses in the L1 will fall on the first cache line. All accesses in L2 will fall on the first cache line. And all accesses in the LLC will fall on the first cache line. So here we are only able to store in the entire cache hierarchy 8 plus 8 plus 8 24 cache lines total out of many megabytes of cache capacity. Right, so that's the deal with cache associativity. Usually it doesn't end up hurting you. Usually it's only when you have these well-spaced, power of 2 spaced really, accesses. So to give one more example, say we space them out our accesses are spaced out 4 kilobytes plus 64 bytes. So what is that? 4096 plus 64. 4160 apart. Well, then the first one will be here, and the next one will wrap around and be the next line in the cache. And the next access will be the next line in the cache, right? So now we're suddenly using the entire cache again. Yeah. So usually you don't run into it. But then when we're dealing with page size allocations like we might in an operating system, or if you're writing our own memory allocator, then it becomes a very important issue. So it's definitely worth keeping in mind. That's all.